Hello class, this is section 7.5 and in this video we are going to discuss the self-adjointness of the Laplacian. So let's consider the Helmholtz equation again and recall that we have these boundary conditions. Beta 1 xy f plus beta 2 xy greater than f equals 0 for any xy on the boundary. And let's also recall the Green's formula that we just calculated in a previous video. And we'll say that the Laplacian is self-adjoint if the Green's formula equals to 0, or rather the left-hand side equals 0. If you may remember, what self-adjointness means is that when you're multiplying u and v, applying the Laplacian to v and applying the Laplacian to u gives you the same thing. And the multiplication that we are defining it over is this double integral on R. So we need to figure out when this is 0, but that's the same thing as figuring out when the right-hand side is 0. So let's do that. And we have, remember, some boundary conditions, and this gives us some restrictions on u and v. Beta 1 xy u xy plus beta 2 xy gradient of u xy equals 0, and the same thing for v. Now let's assume that beta 2 is non-zero. This isn't really necessary, but this proof also works if beta 2 is 0, but it works a slightly different way. And just to make things simple, we're just going to make that assumption. But when that happens, we can do this. We can write down gradient of uxy as beta 1 xy over beta 2 xy, since beta 2 is 0, times uxy. And same thing for v. So if we plug that in to the right-hand side of Green's formula, this is what we get. We write down u, but instead of the gradient of v, we have beta 1 over beta 2 times v minus v, but instead of the gradient of u, we have beta 1 over beta 2 times u, dot product with the normal vector, ds, on the boundary. But this is beta 1, beta 2 these are all functions, so they clearly cancel out. We get 0 dotted with the n with the normal vector, which is clearly just 0. But this implies that given these boundary conditions, our Green's formula gives us 0, and therefore we have that the double integral on the region of u Laplacian of v minus v Laplacian of u is 0, which implies that the Laplacian is self-adjoint, which we desired. So if we restrict u and v to having these boundary conditions, our Laplacian will be self-adjoint, which allows us to apply very nice tools and theorems on the Helmholtz equation.